Today we'll start off with Bayes' theorem and then go to the very essence of machine learning. So how good can a classifier possibly be? The nice thing is that we will get an answer that is easy to formulate. The ugly thing is that it will depend on knowledge of the true density, which of course we don't have. We always only have a finite training sample. But we'll come to that later. So let's start with Bayes' theorem. You remember when we talked about random variables that we had this event space. You also remember that this was a capital omega. And we talked about different events. And for example, I'm creating artificially here some event alpha. And let's say that this probability of alpha is 1/3 approximately. Let's create an event beta. Let's say that the probability of beta is 1/10. It's maybe a little bit small. Maybe I should have done it a little bit larger. But the important thing is that the way I draw beta here, I'm making sure that half of it intersects with alpha and half of it does not. Okay? So we have this event beta. And we can, I could color code all of this if you like. The probability of alpha, the probability of beta, we just measure by their area. But I could highlight, let's say, this area of overlap here. Yeah, so this green thing would be the probability of alpha and beta. And the question is, how can we relate it to these quantities that we do know here? Let's say that this probability of alpha and beta, if beta was 1/10 and if this was half of it, then the probability of alpha and beta would have to be 1/20. All right. Now, we can ask how this relates to conditional probabilities. And the conditional probability is written as follows. We say P of alpha given beta. Yeah? So in words, this would be the probability of alpha given beta. Or we can call this a conditional probability because we condition on beta. And so let's say I know that beta holds, then I know that I'm somewhere in this part of event space. And then we can ask, given that I know that I'm somewhere in beta, somewhere in this event space, what's the probability that actually alpha also holds? So in this case, this would be the probability of alpha given beta, which would be, if I already know that beta holds, we've said that this would be 1/2. That's the result. That's the way I've sketched it here. But it would be nice to relate this to these other quantities that we've seen here. Yeah? So one way to argue is that I divide this joint probability of A and B by the probability of B. Or alpha and beta divided by the probability of beta. So let's just check. Alpha and beta, here it said was 1/20th, and probability of beta was 1/10. So this is 1/2. Or we can argue the other way around. We can say that the joint probability of alpha and beta is the conditional. Times the probability of beta itself. I think that's maybe the formula which is, maybe that's the most intuitive one here. So probability of alpha given beta, we had argued was 1/2. You know, just estimating visually. So if we know that we are in beta, then there's a chance of 1/2 of being on either side of this dividing line. Yeah? So let's say this is 1/2 times the probability of beta itself was 1/10. And we again get 1/20. So the numbers at least seem to match up. So I've here given more or less a geometric argument. The formulas are also compatible. So if I multiply this formula here with P of beta, then on that side I remain with the joint probability, and then on the other side I get this times the probability of beta, which is the same thing that's written here. So in fact, we can factorize it the one way around, or we can factorize it the other way around. I can say this is probability of beta given alpha times the probability of alpha. It's symmetric. And this equation here is the foundation of Bayes' theorem. From this equation here, we can either divide it by alpha, or we can divide by the probability of alpha, or we can divide it by the probability of beta. And then we get this statement here that the probability of alpha given beta is probability of beta given alpha times the probability of alpha divided by the probability of beta. Okay, so this is Bayes' theorem. It's a very celebrated result in statistics. As of now, it's completely abstract, but we will bring it to life in the context of classification. By the way, the same argument works with more than, or this type of expression here. I can write with more than just 2 events. So if I do it with more than 2 events, this is called the chain rule of probability. Which states that if I have a probability, let's say the joint probability of alpha and beta and gamma, and by the way, when I write a comma, this is the same thing as saying probability of alpha and beta and gamma. It's the very same thing, just a different way of writing it. Then I can factorize it as the probability of alpha given beta and gamma times the probability of beta given gamma times the probability of gamma. Or I could factorize in other ways. I could say it's the probability of, whichever way you want. I can say it's the probability of beta given alpha and gamma times the probability of alpha given gamma times the probability of gamma. Or there are more ways of factorizing the very same thing. One consequence is that when we write an expectation with respect to two random variables, let's say alpha and beta, then in the context of kernel density estimation, we had an expectation that was with respect to more than one random variable. And at the time, I just wrote expectation of alpha, expectation of beta, and then the argument. And the reason I could do that at the time was because we assumed that those samples are sampled from the underlying process independently. But in general, when there can be dependence, I have to say that I take the expectation of alpha and then the expectation of beta conditioned on alpha of whatever quantity I want. So this is the chain rule that leads to this kind of statement. Okay. And this Bayes theorem is really important when we discuss multivariate distributions. And here we, in case you don't know them, we will introduce a few new technical terms. So multivariate is just statistician speak for multidimensional, what a distribution is, you know. And I have a pretty picture somewhere. Here I have a, some discrete distribution involving two random variables. You can see that they're not independent. So this thing here would be called the joint distribution. If I'm calling the variables A and B, then this would be described by a probability density of A and B. Or if you prefer, probability of A and B. And this, like every distribution, this thing is normalized. So if we integrate this over both random variables, then we would get 1. So if I take the integral of, or the summation, if it's a discrete distribution, of the probability in A given B over A and B, then this thing would be 1. But sometimes we can be interested in only one of, in the distribution over just one of the random variables. So for example, let me call this axis here A and this axis here B. Then what you see on the side here is the marginal distribution. Margin in German is der Rand. Randverteilung. And we write this as the probability of A. Or this would be the marginal distribution P of B. And it's a bit sloppy that these are here drawn in the same diagram. So, I draw a separating line here to just show that these are not part of the joint distribution. It's just, created in a single plot here for convenience. Well, and this marginal distribution, we can obtain it by integrating out the variables that are not of interest. So the probability of B would be the integral of probability A and B, where we integrate A out. This is for a continuous, or for a discrete distribution, you would have the probability of A and B, and you sum over all A's. This would be continuous, this would be discrete. Here I've given the continuous formula. So we have joints, we have marginals, and these are terms that you will really, really need to remember by heart. Yeah? What they mean and what they are, and how they relate. And the final quantity that we have here is the conditional distribution. I can say for a given value of A. So let's say that we fix A at this level here. Then I get a distribution which is only a function of B. And you know, I could plot it here. And this is the distribution that I'm not sure if my plot is great, but I hope you know what I mean. This thing here would be the conditional distribution P of B given some A. For example, here A was whatever, 1, 2, 3, 4, 5, 6, 7 or something. And then the Bayes theorem still holds. So we can say that the probability of B given A is the probability of A and B divided by probability of A. Okay, and these are quantities that we will work with a lot in the future. Do you have any questions for them? Yeah. What means P, A, and B? Okay. All right. So I'm trying to find a good example of what could this histogram possibly describe. Making up a really stupid medical example. Yeah? Let's say we have a cohort of patients, and for these patients, you have measured, let's say, maybe the blood sugar level. Perhaps you're interested in whether they're diabetic or not, and this would be blood pressure. Let's say, okay, so we would have blood sugar, blood pressure, and then what this joint distribution describes is we have this cohort of patients, with this group of patients. What is the probability of finding a patient who has this much blood pressure and that much blood sugar? And then this is given by the height of this white bar that you saw. So here it would mean, we have no people with this combination of blood sugar and blood pressure, but we have quite a few people with that combination and quite a few people with that combination. Okay, so this would be the joint distribution. And then we can condition. Let's say we're only interested in people with this level of blood sugar. What is their distribution? And then we look at only this line. Okay, let me make this picture here a bit prettier. Let's say we are interested in this level here, so 0, 0, 0, and then we find here we can't really see what's happening. Looks roughly like that. Yeah, so that would be the distribution for a given level of A. Do you want to ask again? Do you want to ask again? Is it clear? More questions for this? All right. Good. Equipped with this, let's go to statistical decision theory. So if there is, I like to think of it as, don't quote me on this, but I like to think of this as the Schrödinger equation of machine learning. Or of classification at least. And there's no Hamiltonian in there. But what I try to say, it's a very basic equation that has a rich interpretation or many consequences. Yeah? What we're going to look at is the risk of a classifier, so how good a classifier is, and we will answer the following questions. So the questions that we have are, firstly, what does the best conceivable classifier look like? And we will give an answer to that. And the second question is, and how good is it? So best conceivable does not necessarily mean perfect. And by the way, this best conceivable classifier is called the Bayes classifier. And how good it is, this is called the Bayes risk. Terms which I'm going to define further down. And by the way, Bayes was a person, a reverend, so member of the English version of what the Protestant church is. And his result was corrected and popularized by somebody called Price after he died. And it's, very fundamental, this role of Bayes in machine learning in general. Okay, so we will today look at a statistical model of classification, and I could describe it as follows. I can create a recipe of how do we generate a training set. A training set, or more generally speaking, an observation x, y, where x is always the features or the attributes and y is the label. Yeah? And a simple model would be as follows. First, we sample a class, and let's say we have just two possible classes, but then we need to sample the classes with a certain probability. Yeah? Sample a class with what's called a prior probability. Now, we could say, for example, the probability of class 1, I'm making this up now, would be 0.6. And because this is normalized, we would find that the probability that y2 is the other class would be 0.4. Yeah, because this must sum up to 1. So we sample a class. And then secondly, we sample features or attributes, but given that class. So if our, hopefully the two classes will have different distributions in feature space, or else our task is hopeless. So if I were to make a picture, I would say that we have, let's say, two-dimensional feature space, x1, x2, x1, x2. And I'm now making up some distribution. Let's say that this here is for class 1. Let's say that this is for class 2. And so our first choice or our first step here would be, well, we throw a dice, an unfair dice to decide from which class are we going to sample. And then given that class, we're going to sample from this distribution. And this distribution, you know, it could look like anything. I'm inventing a distribution here. Let's say this is the distribution of class 1 in feature space, and class 2 will hopefully have a different distribution. Or maybe that looks like this. Okay, so this is the kind of statistical model that we have in mind. And then we can talk about, now that we have distributions, we can talk about expectation values and such. Now, to define the risk, we need the notion of a loss function. The loss function, and now we come to your notes, which you have on your paper, by the way. These loss functions just tell us how bad is what kind of mistake. So this loss function, capital L, has two arguments. The first argument is the true class, and the second argument is the predicted class. And some mistakes are worse than others in general, in real life. Huh? So let's say if you are developing a medical test, let's say, then if your test gives a false alarm, this is not great. But you can, let's say you have a really cheap test. Yeah? So let's say you develop a smartphone app. It looks at whatever. It looks, let's say you develop a smartphone app. It takes a picture of your skin and decides if this pimple is a skin cancer or not. Yeah? Now, sometimes the app will make the right prediction, and sometimes it will necessarily be wrong. Now, there will be two kinds of mistakes. For example, in reality, you don't have skin cancer, but the app predicts that you do. Now, this is not a fantastic outcome because it will make you nervous, but then you can go, to the dermatologist and have a real checkup, and perhaps they find yes, everything was just fine. Or there's the other kind of mistake, namely that in actual fact the pimple was skin cancer, but your app did not recognize it as such. And the outcome of that could be more severe because maybe the patient trusts the app and doesn't go to see the doctor, and then the person dies and it's your fault. So there are some mistakes which are worse than others. In general, how bad a mistake is, we can summarize in such a table. So this is now the table for my loss function, and you see there are the two arguments. What is the true class? Here I've called the classes just 1 and 2, like healthy, skin cancer, whatever. And here is the prediction. Now this in this table, finding the values in this table is not a task for the machine learner. This is something that the outside world tells you. Yeah? For example, predicting class 2 when the truth is class 1, perhaps that's associated with a penalty of $1,000, whereas this error here is associated with a penalty of only $1, let's say. But somebody needs to define this loss function up front. Generally, when you make the right prediction, so you predict class 1 when the true class is also 1, generally this should incur a loss of 0. Or here, you predict class 2 when class 2 really is what's present, the loss is 0. If we choose this simple loss table here, this is called a 0-1 loss. Okay, the 0-1 loss. Now, the aim of classification is we want to minimize the expected loss. So we accept this table here as describing our loss, and we want to minimize the expected loss. And the expected loss has another name. We can also call it the risk. And now, further up, I mentioned distributions, and this becomes important now because expected loss, I can compute it in terms of an expectation value over some distribution, and this is what we're going to do now. So we define the risk R of a classifier F as follows. We say it's the expected loss. So there's the loss function. Y is now a random variable. X is a random variable. But F is your, and I'm going to assume that it's deterministic now, your deterministic classifier. So F could be, for example, a k-nearest neighbor method, or it could be random forest, or whatever you choose. This would be your classifier. So for some random combination of y and x, this gives you a loss. And now we want to compute the mean or the expected loss, where the expectation goes over the kind of distribution that I had sketched here further up. All right, so far, nothing too exciting has happened. Yeah? We've defined a loss function, and we say we take the expectation because we're interested in this quantity. And we call it risk. We call it the risk of classifier F. But now, what we want is to, well, find the classifier minimizing this. And so we're going to transform this a little. Yeah? So first, we're going to use just the definition of how the expectation value is defined. Yeah? So this is the definition of the expectation with respect to x. See, x, I here assume that it's a continuous random variable, so I take the integral over all possible values that x can take. I'm multiplying with the probability of x, integrating, and this I've just copied down from up here. No? So I've only used the definition of what the expectation value is. Now, our interest is minimizing this risk. To minimize this risk, we have an interest, the risk is an integral over all of space, and to minimize it, we want to make this as small as possible at each and every point in space. So in the next few lines, we're going to look at this quantity here. Here I've just copied it down. I've only repeated what was written in the integral here. And now what do we have on the right-hand side? The expectation of y given x is, so we sum overall, because this is now discrete, capital Y is the set of all possible class labels. In our example above, where we had just two classes, this was just 1 and 2. And you see that on the very right-hand side, we multiply with the probability of y given x. So what we've used on the one hand was the definition of y given x on the one hand. And now on the other hand, we want to incur, we have this second summation here over the possible labels. And we charge a loss of the truth is y and our prediction is z. But of course, we want to charge this loss only if this is the prediction that we're actually making. So this is an indicator function here. Indicator function, which is 1 if f of x equals z and is 0 otherwise. So we're interested in the expected loss here, and we charge this loss only for that class z, which our classifier f of x actually predicts. Yes?
This is many handouts. So
I made 60 copies. Great.
I'm not the only one. I think the role also has own one.
Okay, so people who use electronic devices, could they maybe pass on their paper versions in this corner? Great, thanks. The 60 was a compromise between how many people in the room and how many trees do we cut down. Yes, question. Okay, paper there, please. Who needs more paper? Okay. All right. Look, if we're short of paper, I will put this annotated version then in the OneNote, yeah, that you all have access to. Good. So we've just finished with this line here. I know it's difficult to digest when you see it for the first time. Are there immediate questions for this line? Yes?
The identifier function, the chronic delta? Basically, that's the same, right?
Yeah, I could have written chronic delta here. So, the chronic delta is usually 1 at 0 and 0 elsewhere. And this is 1 when the argument is true and 0 elsewhere. Yeah? So it's very similar, but it's not the identical thing, I would say. Yeah? There was another question? Okay. Good. Now, so far, I've just written L. Yeah? So this was true for any loss table that we can possibly invent. But now we're going to instantiate this formula with the 0-1 loss that you've seen above. So 0 mistake or 0 loss whenever the prediction is accurate, and a constant loss of 1 whenever you make the wrong prediction. Now we can look at this formula and ask if I get a penalty of 1 whenever I make a wrong prediction. And then I can write it as you see here. So let me scroll back up to the loss table. We had the 1s in there. And let me make the 1 here maybe thick purple. 1, 1. It's the same 1 that we see here. So now we sum over all possible labels except the one that we predict. And we get a loss of 1, multiply it still with how likely is it to get that label. So with probability y of x, we're getting a specific label, and now we're summing over all the other labels, and each of these other labels must be wrong, which would give us a contribution of 1. Now this is the conditional distribution, which is again normalized. So I know that the sum over p of y given x, if I sum over all y, is 1. And here I've summed over all p of y given x except for this one. And due to this normalization constraint here, I can rewrite it on the right-hand side like so. Okay, so let's remember what's written on the left-hand side. On the left-hand side, we have the expected loss if we make prediction f of x. And on the right-hand side, we now find that this is given by 1 minus the posterior probability of f given x. And if we go further up, what we started with was the risk of the classifier. So we wanted to find the f which makes this thing as small as possible. Then we looked at the kernel of this integral here, and below here we worked with this kernel. So we still want to make that kernel as small as possible. So in other words, I want to make this thing here as small as possible. Well, and to make it as small as possible, p is a non-negative quantity. I want to make that as large as possible. Okay, that's what I've written here in words. To minimize this conditional expectation here at each point x, we choose the f of x, which maximizes this. In other words, I want to predict the class with the largest posterior probability. I want to predict that class which has the largest probability at some given feature attribute x. Let me scroll back up. Let's look at this picture here. Let's say if I've taken this point x here. Well, which class, assuming the prior probability here is, let's assume the prior probability here is the same, which class is stronger, or which class has the higher probability at this location? This thing here, yeah? Because this is like, so high, whereas that is only so high. But if we choose another observation, let's choose this observation here, then for class 1, I get that much probability, but for class 2, I get this much probability, which is more. So in other words, here, at the blue location, to minimize my risk, I should predict y equals 2, but at the green location, I should predict y equals 1. Okay, I'm scrolling back down. To the final statement here. For the 0-1 loss, the classifier which minimizes this base risk, or which minimizes the risk, is called the base classifier, and it's given by the classifier which, at a given location x, predicts the class with the largest posterior probability.